Hi, everyone. And with that, we move on to the next part of today's session. We have Abdullah Khalid with us. He will be continuing the quantum error correction module from last week. Everyone who had attended last week, I would just advise you to revise through the notes, whatever you have been doing so far. And Abdullah will be just starting off from where he left, right? For those who are joining it for the first time today, again, I would recommend you to go back to the YouTube recorded lectures and just watch through the last week's lecture so that you can get caught up and then continue the lecture. Over to you, Abdullah.
Thank you, Vardhan. Okay, so let's get started. I see that there's still quite a lot of people here. I think the first thing I want to ask is, do you have questions from last week? Anything particular that you wanted asked, or any confusions in the lecture? I will be reviewing part of the lecture right now. So let's see. Here. I see people. Well, okay. Can Okay, well, if questions come up, I will answer them, but I'm just going to do a review anyway, so of some parts of it, and actually build up on what's coming today. So let's kind of yeah. So last time we said that the way classical error correction works is within this model, at least the simplest kind, where you have Alice who wants to send some messages. So she has a message M, which is some sort of bit string, and she tries to send it. Sorry, 1 second. Okay, so yeah, so she has a message, and the way it gets sent to Bob, in order to reduce the probability of Bob getting the wrong message, is that she encodes it into some sort of code word. That code word goes through some channel in which whatever information she sends experiences some noise, and that noise, changes the code word C, which is some bit string of length n, into a bit string of the same length, but with where we add E to it. So you get the corrupted code word. Now Bob's job is to actually decode this corrupted code word and figure out an estimate for the message. And this is, I mean, the way all of this works is that Alice and Bob have pre-agreed upon some clever encoding that it allows Bob to correct even if some errors occur. Not if a lot. Usually, if a lot of errors occur, then Bob will recover the wrong message. But if only a small number of errors, depending on what method they use, then this decoder will work correctly, and Bob will estimate the correct message. So okay, I see there's no questions about error correction right now. So let's talk about the classical repetition code, because we're going to talk about the quantum repetition code today. So I want to just review it and talk about some of these things. So the way we said, we also reduced everything here down to linear algebra. And we said that this code word C was equals to M times G, where G was the generator matrix and M was our message. And that's how this encoding works, which is quite a simple process. On the other hand, at the decoding end, the main thing that Bob did to kind of figure out what was going on was that he computed S equals to H times C bar. And the syndrome this was S was the syndrome, which gave Bob information about where the errors had occurred, right? So we did this for the Hamming code. But something we did not do last time was figure out what is H. What is this H, the parity check matrix for the repetition code? Okay. So let me remind you what the repetition code did. The repetition code did was that it took 0 and it mapped it to 0, 0, 0, and it took 1 and it mapped it to 1, 1, 1, right? And then, for example, if so, these are my code words, right? So this is M and this is my C, for example, right? And similarly for the other guy. And for example, we said that a possibility of the error could be that, let's do it from here, that if, for example, Alice is sending the 0 thing, then, the error that could happen is that, for example, this became 0, 1, 0, right? Or 0, 0, 1, or something like that, right? So now what is H for the repetition code is my question. You're welcome to answer in Discord. So I can remind you of the, sorry, there's a transpose sign here that I forgot about. So H is actually, it has n minus k rows and n columns. Right. So in this case, we know repetition code has, well, so the repetition code n is 3 and k is equals to 1. So you get 2 columns and then you get, 3 rows. So H is the matrix. What do you think should be the entries here? So that, for example, as different errors occur, you get the correct syndrome, Yeah, so remember that we did some parity bits for this. So let's go back to for example, the notebooks. So we figure out that this was the parity matrix for check matrix for the Hamming code, where we built it using this guy, right? We said that the checks that that Bob does is that he compares these guys, like he computes the parities of these message bits again, and compares them with what Alice said. So the different columns here corresponded to that operation. So for example, the first column here corresponded to the operation that Bob was basically checking the parity of, sorry, the first row. I'm reading it wrong. So the first row said that Bob is checking the parity of M1, M2, M4, and comparing it with the parity bit P1 that Alice sent, and similarly the other rows. So in the error correction scenario, the way we just initially thought about it was that we said let's apply a majority voting kind of scenario algorithm to whatever Bob receives. So example, Bob receives 001. What Bob will do is that he will count the number of zeros and count the number of ones. He recognizes that more zeros than ones, so he will say that actually what Alice meant to send was 000, which means that the message was actually equal to 0, right? But the majority voting algorithm is actually not very linear algebraic. It's not. So let me propose a different kind of thing. So suppose that your code word so is 001. Okay. We want to compare the values of different elements of the C in order to figure out where the error has occurred. Okay. Not only that an error has occurred, but where has it occurred as well. And the comparisons we will make is that we will say, hey, look at and compare the first two guys and compare the last two guys. Okay. You can see that, I mean, let's actually look at some examples. So C tilde is, for example, this no error case, or C tilde is 010, or C tilde is 100, right? And then take an example which is bad error, right? So 2 errors or even 3 errors. Okay. So these are bad examples. These are things that will be corrected. These are things that will not be corrected correctly. But let's see what happens. So in every case, what we are doing is we are comparing the first two guys and we're comparing the last two guys. So right. So you can see what will happen. So if you look at the no error case, right, and things are completely symmetric for the 111, it doesn't really matter. Everything will flip out. So you can see that if you compare the first two guys, they will be the same. And if you compare the last two guys, they will be the same, right? So that might be an indication that there's no error. But now look at this guy. So if the first two guys are the same, but the last two guys are different, okay? So if you think about it in terms of majorities, the only way that these two are the same and this is the different is that these two have actually the same value and this is a different value, right? So this tells us that it's the last value which has an error on it. Similarly, you can look at over here. So if this is what Bob receives, he compared the first two and the last two, he says that both of them are different, right? So first and second guy are different and second and third guy are different. And the only way that's possible is that if the second guy is actually different from the first and the third guy, and the first and the third guy are actually the same, right? Remember, there are only two possibilities, 0 or 1, where every item in this list can either be 0 or 1. So if the first and the second item are different and the second and the third item are different, the only possibility is that they are 0, 1, 0. Obviously, if Alice sent 1, 1, 1, the same kind of thing happens in the other case, right? So if Alice, for example, sent 111 and what Bob received was 101, then you can see that comparing the first and the second guy, second and the third guy, tells you that it's the middle guy which is different, and the first and the third guy must be the same, right? So and you can we can keep going down this list. So if you look at this, so you see that this is the converse of this case, that if the first two guys are different but the second and third guy are different, then that tells you that it's the first guy which has an error. So we want to apply this kind of thing because comparison, we said, is just parities, right? So when I say compare, I'm just computing the parity of these guys. If the parity is 0, I'm counting the number of ones in each of these. So I count the number of ones in the first two guys, it's actually 0, which means the parity is 0. Over here, if I count the number of ones in the first two guys, I have 1, 1, which is parity of 1. And similarly over here. So the way that we can actually write that down is we can say that I want 1, 1, 0, and 0, 1, 1 as my columns, right? So now you can see, for instance, that if I multiply it with this guy 0, 0, 1, I will get 1 into 0, 1 into 0, 0 into 0. So the first guy is 0, and then 0 into 0, 1 into 0, and 1 into 1, which gives me 1, right? So 0, 1 is an indication that it's, so you can again tabulate all the possibilities and kind of look. So you what we will end up getting is that that possible syndromes are 0, 0. Again, I'll start writing them as bit strings, right? So over here, this was my S, and sorry, I pressed down my button. So S equals to 0, 1, S equals to 1, 0, S equals to 1, 1. So you can compute that this means no error. This means that, we just computed this possibility, right? Error on the third guy, right? So this is actually error equals to, this is error equals to 0, 0, 0, and this is error 0, 0, 1. And this is, if you compare, this is actually 1, 0, 0. And then if you compute all of these, you should do them yourself. This will be the scenario that, if this is the error, this is the syndrome you get. Maybe this is a two-way relationship, not a one-way relationship. Okay, so does this make sense? That this sort of comparison is also like, instead of doing majority voting, we can do this comparison of values, and that also tells us the location of the error. So I see one person is typing, so I'll just wait for them. Really, you should be asking more questions. We are going to use this comparison technique again in the quantum repetition code, which is just coming up. Okay, I see that there are, perhaps everybody agrees. You can always just say in Discord that you understand and you agree, which okay, so I'm just going to move on under the assumption that people understand. If you don't understand, not very good. Let's move on to the quantum error correction case. Okay, so the scenario of under which that Alice and Bob communicate is much the same as in the classical case, except now, if instead of sending bit strings as messages, what Alice wants to send is some sort of a state, quantum state, Okay, psi k. So k refers to, okay, so I should say state of k qubits. Okay, for simplicity, you can generalize this idea. We generalize this idea to qubits or any other sort of quantum state if we want to. But yeah, like for now, we will just think about qubits. So we are gonna you have the state of k qubits which Alice wants to send, and as it goes through this noisy channel, the error it will experience will be some quantum operation E. Okay, so this is some generic operation E, and what Bob receives instead is E times psi k, right? So and if error the operation is not identity because of the noisy channel, then Bob will will get the wrong message. We can kind of get a sense of this. For example, let k equals to 1 for now, and which means that I only have a state of 1 qubit, right? So let me just say this is my state, right? This is the arbitrary state of 1 qubit, and then assume E is the X operation. Well, so actually, let's go over both possibilities. So assume, okay, so let E equals to identity and E equals to X. So just as an example, we can look at more possibilities. We can look at something like this. So you can see that what Bob receives is actually just psi, right? But in this case, Bob will receive alpha 1 plus beta 0, right? And if the error is something like this, which is a z, Bob will obviously just receive alpha 0 minus beta 1, right? So these are different possibilities, and these are not the only kind of errors that could occur. But I mean, let's talk about these first. So you can see that if either X or Z can Z errors can occur, then what Bob receives is a very different state from what Alice sent, right? And in this naive thing where Alice and Bob are not using any sort of error correction, then Bob has not the slightest clue whether an error occurred and whether that or if this is what Alice wanted to send. So I mean, if errors have some probability, then with whatever that probability is of an error occurring, Bob will receive the wrong message. So what we want to do is we want to come up with procedures that improve the possibility that Bob receives some errors or receives the correct state. Okay, and we want to design these procedures for any generic sort of noise. So what other sort of noise could basically occur? So this X gate noise I will continue to refer throughout today and in the notebooks as bit flip errors, okay? Because that's a nice way of saying it instead of X. And Z is actually a phase flip error, right? Because the phase flips from plus to minus or minus to plus. So you get bit flips or you get phase flips, but you can also get other errors. You can get, for example, an arbitrary rotation on the Bloch sphere. If you remember your QBronze, remember that you could rotate your state on the Bloch sphere around any axis. So you can think of rotations around the x-axis. You can think of the rotations around the y-axis. You can think of rotations around the z-axis, right? You can think of all sorts of other possibilities as well. So the question is an operator, is there a super operator in the scheme? So that's an excellent question. So if you're already familiar with quantum mechanics and well versed with it, in general, E will be a super operator here. But if you don't know a lot of quantum, that's totally fine. Just thinking about these cases will actually be sufficient. And in fact, what we'll argue is that just think about X and Z errors is actually sufficient for a lot of error corrections in qubits. So we'll just like if you can, basically there's a very nice result which says that if you can correct these bit flips and phase flips using your code, then you can correct any sort of errors. This is a very nice property of quantum mechanics and quantum error correction. But we'll get to that eventually. So Mohammed is typing again, but I'll wait. I'll continue. So so now what we're going to do is that we are going to use some sort of, so here what we did was, I should say that no error correction, right? This is the no error correction scenario. And now when we go here, so we will say, hey, we are actually applying some sort of error correction, right? So much like in the classical case, what we will have is that there's a message source in which Alice is trying to send out psi k, and there'll be an encoder. This will be some sort of mini quantum computer that will apply some operations to the psi k, and instead of having a state of k qubits, you will have a state of n qubits, which will be the called the code word, the quantum code word, but I'll just refer to it as a code word because we'll only be talking about quantum from now on. And when it goes through the noisy channel, an error will occur. There's a mistake here, unfortunately. So this should be n, and this should be n over here, and this should be n over here, right? So the error is occurs, and you get a corrupted code word of n qubits. And then Bob's job is to decode and figure out what the estimated thing is that what Alice sent. So how, right? So we're going to think about how to do this. And our strategy will be much the same as in the classical case. We'll look at some examples, and from that examples, it will we will build up some intuition, and then from that, once we have intuition, we'll start to build up some formal theory. So the idea is that today I'll talk about some very basic quantum codes, and then next time we'll start talking about the theory. So we'll have 2 sessions of theory. It's not very difficult theory. So in the, what is the symbol you're using above the ket for the code word? Oh, sorry. So this is not big enough. I can make this big enough. So it is a bar, just in the classical case, right? So it's a psi bar, and this is psi tilde, right? So sometimes I'll also refer to them orally as that, psi bar and psi tilde. Psi bar is a code word, and psi tilde is the corrupted code word. This has messed with my ends, so the ends go here. Okay, so what we're going to do is we are going to study 3 different codes. So we are going to study the quantum repetition code for that only corrects X errors. Okay, so we'll assume that the only errors that occur inside our channel are X errors. Then we will study a code which only corrects Z errors, and then we will study a code that corrects all errors, right? And sorry, I should say this on well, maybe I won't say here, but write it down. But the error will there'll be a limit to how many errors we can correct. So in these simple codes, we will only be allowed to Bob will only be able to correct if there's 1 error on one of the qubits, right? So not 2 qubits won't experience an error, only one of the qubits will experience an error. So these are 3 ones we will do, and the last one is called the Shor code, which is a very one of the well, one of the first codes that were designed, and which is really very excellent starting ground for studying things. So let's talk about the first one. So I'll refer to it, the one that only corrects X errors, as the quantum repetition code for bit flips. And the way it works is actually quite simple. So you have the message that Alice wants to send, and this message gets transformed into code words like this, right? So the code, so this is the message, is a 1 qubit, and this is, I should say, not just a message, but just the message basis, right? So in the quantum case, so remember in the classical case, we just saw that only two possibilities. Alice can either send a 0 bit or a 1 bit. But in the quantum case, what Alice can send is obviously psi 0 plus beta 1. Okay. And so this guy is actually, I should explicitly state, to send 1 qubit state. Okay. So we are actually just sending 1 qubit state, which is alpha 0 plus beta 1 generically, and it could be any alpha and beta, whatever you want it to be. And the code word will actually, you can see that a state like this will go to alpha 0 0 0 plus beta 1 1 1. Okay. Mohammed Raza asks, why did you exclude the y basis? Was it just a choice? No. So y is just actually x times z, right? So I should remind you that y is just iota times zx, right? I hope that's correct. It's not xz. Yeah, I think that's correct. So anyway, so basically y is just a combination of z errors and x errors. So if I mean, there's nothing interesting about y except that it's a combination. And what we will see is that in the Shor code, that if you can correct the x errors and the z errors, then the y automatically is correctable, the way the procedure works. So yeah, so coming back to the repetition code for bit flips, we have this, and this is our code word, right? So on the left is our message, on the right is our code word, and this is actually going to work. So let's do an example here of an error, or actually, yeah, let's do an example here. So example error. So I can, for example, get x2 as an error, right? Which means that when this is psi n, which we have just computed, and when it goes to the channel, what Bobs gets is something like this. So psi tilde will actually be alpha times x2 0 0 0 plus beta x2 1 1 1, right? Which is actually just equal to 0 0 1 plus beta 1 1 0, right? Now, again, we have the same idea that we are going to compare the values of different bits. So remember, this is quite important thing. Let me go ahead and remind you. If we measure quantum state directly, or qubits directly, we destroy their state, right? You are very familiar with this. So if I have some qubits in my circuit and I measure them, right? So they had some state phi, and if I measure them, I'll get some answer. I'll get some measurement outcomes, which is 0 0 0 1, in this 2-qubit case. But this phi will be destroyed. These qubits will now will have so for example, if my measurement outcomes are 0 1, so you perhaps remember that instead of your qubits in some generic state phi, they will now be in the state 0 1, right? So we don't want to directly measure our qubits in this scenario. If you measure these qubits directly, right, either you will get 0 0 1 or you will get 1 1 0. And sure, you can kind of possibly infer some information from that about where the error was, right? So if, for example, if you get 0 0 1, you can use the classical ID and say, hey, the third bit was different from the first two, which means that third is where the error must have occurred, or it's most likely where the error has occurred. But now you have destroyed your state. What Alice is trying to send, really, when you think about a quantum state, what Alice is really sending is these coefficients alpha and beta. If you measure the state, then alpha and beta are lost. You'll get one outcome in one shot, and that's it. You want to do things in a way that you preserve the value of alpha and beta, right? And to do that, actually, that's what I want to do is we are going to look at scenario. So this is how you do. What we do is a syndrome measurement. Actually, there's one more thing I should tell you before this actually even makes sense. I see I missed a slide. Yeah, maybe I can just do it over here. It's not a difficult thing. My question to you is that how do you construct this? How do you go from here to here? What is a nice circuit that does this? Or from here to here in general? Perhaps that's what we should discuss first. So I mean, what I can think of is that I have some state psi, okay, and I have some 2 ancilla 0, and then I want to apply so this is my psi bar, right? And what I want is psi bar over here. Yeah, so control gates is the answer. And basically the answer is that in this scenario, we will use control X gates. So what I can do is I can do control over here, and I can do control over here, here, and I can do this, something like this. You can see that if psi was 0, then both of these will not trigger, and I'll get 0 0 0 at the end, which is exactly what I get. And if my psi is 1, then I have 1 0 0 here, and 1 will trigger this control gate. So the second qubit will switch to 1, and this 1 will also trigger this CX gate, and you will also get 1 over here. So you get 1 1 1. So you can see that this basis transformation works, and obviously then the linear combination of that basis transformation will also work, right? So you get alpha 0 0 plus beta 1 1. So keeping this in mind, this very simple circuit that achieves this. Let's talk about errors again. So what we are going to do is suppose that on the first 3 qubits, what we get is some psi tilde, right? So, and for instance, psi tilde we said could have been 001 plus beta 110. So this sort of circuit is actually, you can see what we do. We don't directly put measurements on these qubits. That will destroy the state of these qubits. What we do is we use control gates, and control gates, if you think of control X, the role of control X is that it will copy values from over here to here, right? Remember that what a control gate does, control X gate does, is that it takes 0, 0 to 0, 0, right? 0, 1, I mean, these are things, 0, 1 to 0, 1, 1, 0 to 1, 1, right? And 1, 1 to 1, 0, right? But generically, what you can think of, if you look at these, is that it takes, this is my controller, right? That if I have X and Y, what we are going to is X into Y plus X. Again, where this modular 2 X is what is happening, right? You can see that if the first guy is 0, then we are adding nothing to the second guy. So second guy remains the same. But if the first guy is 1, we add it to the second guy. So 1 plus 0 is actually 1, and 1 plus 1 is actually 0, which is what we get. So this is kind of a copy and add operation, or add operation, right? And if, in fact, the important thing is if these guys are actually just 0 and 0, right? So then in our control gate, this Y is actually 0, right? So basically, we are taking X and we're copying it on to the second guy. So this is exactly what happens. What we do is we take the value of the first qubit and we copy it into this extra ancilla qubit. We take the value of the second qubit and we copy it onto the same ancilla qubit, right? So if you look at this and you look at this, it's quite clear what is happening, that you're gonna add the value of the first qubit over here and add the value of the second qubit over here. So you are basically adding the value of the first 2 qubits over here. If both of them are 0, then you're adding nothing to them and you will get an outcome 0. If one of them is 1, right? For example, if this guy is 1, then you'll get a 1 down here and a 0 from here. So you get 1 plus 0, which is 0. And you, 1 plus 0, which is 1. So you get an outcome of 1. And if you, for example, get both of them equals to 1, then both of them will be copied down. And, you will get 1 plus 1, which is equal to 0. Right? Or the other way of thinking is that if both of these are 1, then you get 2 flips. And obviously, flipping 0 twice actually just gives you 0 back again. So what we are just doing is we're copying what we are recording in these ancilla qubits is not the value of each of these qubits. What we are measuring, what we are putting in these ancilla qubits is whether the first 2 qubits are the same or different, and whether the second and third qubits value is the same or different. Right? So I mean, it might be useful if I do something. Let me. Yeah, let me do a simple example at least once, just so we are clear on what is happening. So let me do this over here. Let's do the simplest example, which is that psi bar was actually equal to 0, 0, 0, right? So which means that alpha equals to 1 and beta equals to 0, and then psi tilde was equals to 0, 0, 1, right? So this is what goes over here, that you have 0, 0, 1 here. These guys are 0, these guys are 0. You can see that this means that this one does not trigger, this one does not trigger, this one does not trigger, only this guy triggers. So ultimately what you get over here is that you have 0, 0, 1, 0, 1 as your the value of your 5 qubits, right? So this is and basically a nice way of writing it down is to say that this is psi tilde and this is your syndrome. And then you measure the syndrome. So basically what you get over here is that you get the value of S, which is in this case equal to 0, 1. Right, and just in the as in the classical case, we will say, hey, that means that it is a third qubit, which had an X error on it. So I don't see a question about this. So let me go back to this guy and say that, hey, if things work for the basis states and simple non, if you can show they work for all the non-superpositions, then because of the superposition of quantum mechanics, everything being linear, it will also work for superposition. So the same thing happens here. You can see that you can look at either this or this. The key idea is that the value of the third qubit is different from the value of the first two qubits. And that means that what you will indeed get is that these guys will remain in psi tilde, and these guys, the measurement outcomes over here will be 0, 1. Okay. Because I mean, you can see that because this is 0, 0, I mean, if you look at the first basis, we said that only this CX gate triggers. So which is why the value over here is 1. But you can also look at this guy and you can realize that this is saying that the first two the CX gates on the first two qubits will trigger. So this will trigger, but two triggers will return the value of this to 0. And then this will trigger, which will set the value of this to 1. Actually, this will not trigger, right? So either this will trigger or these three will trigger in the different parts of the superposition. And in all of those cases, what the outcome is that this will become 0 and this will become 1, but this will remain the same, right? So the important thing is that does not change, right? This is which is a very critical thing that we want, that we don't want psi tilde to change. We don't want to destroy the superposition. We want alpha and beta to remain. So now, if we know that that it is the third qubit which experienced error, what we can do is, right, this tells us third qubit had error or had bit flip, right? Apply x3 to correct. Sorry, x2. Yeah. So I did not make a mistake. So x2 to correct. So what I can just do is I can apply an x2 gate over here, and that will return the state back to the original state, which is what Alice meant to send, which is alpha 0, 0 plus beta 1, 1. I hope people are still with me. Yeah, so David asked what will be the full decode circuit for Bob P. So what we can do is we can draw it perhaps. So, I mean, let's draw the whole thing. So, encoding on, right? So, encoding for Alice was that she took psi 0, 0, and she did x and x. There's a control here, there's a control here, right? And then what she does is she sends this through her channel to Bob. What Bob does on his end, right? So this is Alice. Bob, what he does is that he takes 2 additional qubits, right? So what he receives is psi tilde. He adds 0, 0 to it. He does x, right? This is the Bob syndrome circuit that we just looked at. He measures these guys, right? And then conditional, and S is what comes out over here. So apply. So this tells us that apply xi depending on value of x of s, right? And then so you will get for example, I mean, I will draw it. For example, s equals to 1, 1 implies that x1 is what is being applied, right? So there'll be an x over here, and then her decode circuit actually will be at this point. If she does this, she will get psi bar back, and the way to go back from psi bar to psi is to actually just reverse the circuit. If we just run this circuit in reverse, you know, we will get back psi. So what will happen is that you first do a control x from over here, and then you do a control x from over here. Okay, and the outcome of this will be that Bob will receive psi on this over here. So the question so Bob would need 2 classical bits to do error correction. Yes, so you also need a computer that can store at least 2 classical bits and process at least 2 classical bits. I don't think that's too much to ask. David, can Bob decode without measuring the ancillary qubits or auxiliary qubits? No, so it is quite important. Like you can't really do error correction without measuring the ancillaries. So in this case, actually, it's possible to do it. But you should not take that as a lesson. We will very quickly go to codes in which it's not possible to do the decoding without measuring, and the measuring is actually quite important. You'll see. This is slide. So some people are asking questions. We will yeah. I can actually answer that right now. So let's see. I just need to go over these. Actually, so this one I already did. So this I can delete. This is actually, I mean, properties. Should it be x30, x31, x41, x42 instead? Did I make a mistake of some sort? Sorry, what should be, David, what should be x30, x31? So this is 0, 1, 2, 3, 4. So are you saying that, oh, do you want to flip the control gates and control them over here and put the X over here? Is that what you're saying? I think that's what you're saying. So you're saying that should it be flipped? No, we want to actually copy the values of these qubits down to over here. And the only way to do that is to put the control here and the X gate. We'll actually see that there is a flipping that happens, but that flipping will, I mean, that involves additional gates as well. Why are we adding post gate to the message qubit? We didn't change the merge gate, right? So there's an error here. Remember that there's an error of some sort here that a distorted psi to psi tilde. Bob, with this part of the circuit, with the syndrome measurement circuit, is going to determine where the error has occurred, right? So this S will tell him where the error has occurred. So if the error has, for example, errored on X1, he will apply an X gate to fix this, right? Part of decoding is actually fixing the corrupted code word to the corrected code word. And this X is fixing it to the correct code word. Once he has fixed it to the correct code word, then he can reverse it and get back psi. Yeah. So, I mean, it's not easy to say this, but I can, for example, I can put some conditional on here. So, or I can do this, right? So double lines are typically used to indicate some sort of, but I mean, this is not really nice. I should not say that. So maybe this is better. So I can put it in pockets and I can say that condition on F, I apply some sort of decoding or correction, right? So this part is my correction, right? And this part is my syndrome measurement. Okay, so yeah, let me do one thing and then we'll come back to Mohammed Raza's question. So in the same way as we like did in the classical case, we should just think about the probabilities as well. That you can see that if we are only talking about X errors, then these are the different possibilities, right? Either no error or X, a single qubit error or 2-qubit error or a 3-qubit error. These are the possibilities of the errors. Each of them has some associated probabilities. And the output state, if input is 0, 0, 0. We just have to think about the basis states. Is 1, 1, 1, right? So you can see, for example, that if there's no error, then my output state will be 0, 0, 0, right? And then let's think about this guy. And then this guy is telling us that 1, 1, 0, right? And think about this guy. This is 1, 1, 0, right? So I just want to compare that if my input is 0, 0, 0, and I actually get a 2-qubit error on the first two guys, obviously my output state, and by output state, I mean the output of the channel, right? So the output of my channel will be 1, 1, 0. But if you see that if input is actually 1, 1, 1, right, 1, 1, 1, then if I get a single qubit error, then I also get 1, 1, 0, right? And you will see that this will, this sort of, if you fill out this whole table, you will see that there's this confusion that occurred, that if 1 qubit errors also look like 2 qubit errors, right? We saw this in the classical case as well, and then obviously as 3 qubit errors as well, right? So this will turn into 1, 1, 1, and this will turn into 0, 0, 0. So a critical lesson is that this code can only correct one a bit flip at one location. Okay. So I don't see a question about it. I think this is quite a simple point to appreciate. So let's move on. So Mohammed Raza asked, I think I should say something about this. I didn't really plan to. That I mean, this was a follow-up to the question that why do we have to measure? Why can we not do some quantum gates up to over here? And the answer to that is that perhaps, this is important, errors beyond xi. Okay, so imagine, an error that could occur, for example, which is not an xi error, is, for example, the rotation around the x-axis of some angle theta, right? You did this in bronze or something, where you talked about in the block Sapphire, you can rotate your qubit by arbitrary angles theta. And this, if I remember correctly, is actually, I don't remember the sines and cosines, so let's just look at them. Cos, yeah. So this actually, as an operation, is cos theta I minus iota sine theta x, right? This is the definition of this operator, Rx theta. So you can see that if and I can put an I here, and I can put an I here to indicate that on which qubit this is acting. So we can think, for example, what happens if I do Rx I on my psi bar, right? And let's think about, again, like an example, let's do it on the 0th qubit, right? So what will end up happening is that I'll get cos theta psi bar minus iota sine theta x0 acting on psi bar, right? I hope everybody's with me. Now, this is my state at this point, right? After this channel, what Bob receives. Now think about what happens when it goes through this process. When it goes through this process, everything is linear in quantum mechanics. So this part will go through the syndrome measurement circuit, and this part will go through the syndrome measurement circuit, right? And we'll just kind of look at this linear superposition of them here. So when I only look at this part of my circuit over here, right? Just the I've not included the measurements here, right? When this guy goes over here, what is the outcome? You have two additional things here, and the outcome will be that you will get the entire state of these 5 qubits will be cos psi bar s, right? And the s for no error is actually 0, 0 minus iota sine theta, this x naught psi bar, and the syndrome for error on the 0th guy is actually 1, 0. So this is the state before measurement, right? I mean, this is just simple superposition principle applied in for quantum mechanics. You this goes, and then you end up with something like this. Now measure, right? So when you measure this, you're measuring these guys and these guys. So the outcome is that either you will get this or you will get this, right? The probability of getting 0, 0 is actually cos theta square, right? The probability of measuring 0, 0 is cos theta square, and the probability of measuring 1, 0 is sine square theta, right? So, but if measure 0, 0, then my first 3 qubits will be left in the state psi bar. And if we measure 1, 0, then my first 3 qubits will be left in this. So you can appreciate what is happening, that there's this collapse happening of your state into one of the items in your superposition. So your error is some linear combination of identity and an X gate. But after the outcome, after the syndrome measurement circuit, what happens is that your state, your code word state, is either in the with identity applied to psi bar, or it is this, and you know which one it is. If you measure the syndrome 0, 0, then you know your code word has no error on it. And if you measure the syndrome 1, 0, then you know that your code word has the X0 error on it. You don't get a superposition. This is a classical choice of either 0, 0 leading to this quantum state and 1, 0, or 1, 0 leading to this quantum state. So this is why measurement is actually important, because measurements, these syndrome measurements, and projecting it onto some classical bits projects your code words to one of the simple possibilities of no error or X error in this case. And you will see that in general, what happens is that either you get no error, you get the X error, you get the Y, or you get the Z error. One of those are the possibilities that end up happening, that you project it down to these poly errors, and then you can correct further on. Okay, so Mohammed Raza, I hope that I've answered your question. So now he asked another question. The reason that you can ultimately need 2 classical bits to recognize the error might be related to the superintendent's contain ultimately. The reason that we need 2 classical bits is that there are 3 qubits here. The error could have occurred on any of these 3 qubits, or you could have identity. These are the 4 possibilities that you have of detectable and correctable errors. To distinguish between 4 possibilities, you need 2 bits. That's the easiest way of thinking about it, right? So 4 possibilities, 2 bits. And then the general syndrome length formula is n minus k. Yes, the syndrome will always be n minus k, at least for the code we study. Quick question: can we access Jupyter Notebook you're going through on WOMANIUM, etc.? Yes, it's linked on the Canvas course. So if you just scroll down the modules and look at the quantum error correction module, you will see the link. But I can, if somebody can kindly just post the link to that to the repository right now in the chat, that would be great. You need 1 classical bit for each answer qubit. Yeah. In this case, Alice only sends 1 qubit to Bob. No classical qubits are sent. That is well. So Alice is sending 3 physical qubits to Bob, because that's how the state is encoded. But what Alice ends up, but what she really wants, so the message that she really wants to send is a state of 1 qubit. It's also called the logical qubit. So, I mean, I didn't really use that terminology right now, but this guy is called the logical qubit, and these guys are called data qubits, because there are 3 data qubits and 1 logical qubit over here. That's the terminology you'll find in the notebooks as well. Yeah, okay, so there's active discussion in chat. So I'll just wait and see. Interesting questions. Okay, so I think we have caught up with questions. So let me just go on and talk about a different code. And this occurs in much the same way. So now what we're interested in is that we are interested in correcting phase flips or the Z errors, right? And so instead, so think about this. So we have constructed a code right now which corrects X errors or superposition of X errors, or X rotation errors. Okay, now we want a code that only corrects phase flip errors. It doesn't correct X errors at all. There's an argument here as well that why it doesn't correct Z errors. Why this code doesn't correct Z errors, and it's in the notebook. I won't go over it right now. You should work through the notebooks. But this idea that so now we have a code that is only going to correct Z errors and it's not going to correct X errors. Okay, and the way this works is that if Alice wants to send 0, what she will instead send is the state plus plus plus, and if she wants to send 1, she'll send minus minus minus, right? I'm sure everybody remembers that plus is just equal to 0 plus 1 over square root of 2, and minus is just equal to 0 minus 1 over square root of 2. And the way to do it is actually just this circuit, right? So the encoding circuit is actually quite trivial, because you can remember that these 2 X gates will take 0, 0, 0 to 0, 0, 0. And then if you apply Hadamard to each of these, 0, 0, 0 will become plus, plus, plus. And then if you have a 1 over here, right, this is where the psi goes into the first guy. You get 1, 1, 1 over here, and then the Hadamard will convert each one to minus, minus, minus. And obviously superpositions will work as well. So you can see that this circuit works. These are the kind of errors that you have. Again, the idea is that if input is 0 plus plus plus, or the input is minus 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 minus, then you will continue to get plus plus plus, or you will continue to get minus minus minus. This guy, obviously, when you have a Z1 error, remember that when Z acts on the plus state, this plus sign will turn into a minus sign, right? Because Z acting on 0 just gives 0, and Z acting on 1 gives a minus sign. So you get a minus plus plus, right? And on this side, minus will actually convert to plus. Similarly, you can see that you get a plus minus plus and a minus plus minus, right? And similarly, you can keep going down. Over here, you will get a minus minus plus. Over here, you get a minus minus minus. Over here, you get a plus plus plus, right? And so on and so forth. So again, the idea is that that this guy will if the input is minus minus minus, then a single qubit error turns it into a minus minus plus, which actually conflicts with a 2-qubit error on this thing. So actually, you can only distinguish between single qubit errors and not 2-qubit errors. So you can only, if you only have single qubit errors or no error, then you can correct. If you get a possibility like this, then you will actually make a mistake in your correction and you get the wrong answer. But again, the probabilities of this is much lower than the probability of this guy, right? This is high probability, this is low probability, assuming that p itself is small. We've all gone through all of these arguments in the classical case. So that's why it's beneficial to this repetition code is beneficial. Raziel has a question. What if alpha beta change to the channel? Alpha and beta cannot change to the channel in our scenario. What is happening is that operation happens and alpha and beta change in a very systematic way, either as X or Y or Z or I identity. I think we can talk about this at the end, perhaps. So the syndrome measurement circuit for the repetition code is something like this. The idea is that you get psi tilde over here and you have 0, 0 over here, that we will just basically employ the same circuit that we just employed for the bit flip code. But what we'll do is we will just first, right? So suppose this is a plus, you convert the Hadamard will convert it back into a 0. And then we will do this sort of addition, and then we convert it back to a plus. Same with minus. If it's a minus comes in, minus will convert into a 1, which will trigger this X gate, and then we'll convert it back to a minus. So it's kind of a very dumb way of doing it, but that's how you do it. You just take that code and add Hadamards to around everything. And the Hadamard first one goes from the plus minus basis to the 0, 1 basis, and the second takes it back. But you can very easily recognize that this circuit is actually simplified, because what I can do is I can do various operations. I can take this Hadamard over here, right? I can, just for simplicity, I can take this Hadamard to the end. I can take this Hadamard to the end. This Hadamard is already at the end. I can take this Hadamard all the way to the first guy, right? There's nothing else on this line except this Hadamard at the start. So goes all the way over here. So I have 3 Hadamards at the start, this guy, this guy, this guy. I have 3 Hadamards right at the end. It's these guys. And look at these guys. This is an identity, right? So basically, what I end up getting is, I'll just copy it from the is you get something like this, right? So this was identity, and then I've just moved my Hadamards here. So you get this nice circuit where you have a bunch of Hadamards acting. Then you do your classical bit flip repetition code syndrome measurement, and then you go back to Hadamard, and then you do your measurements. Okay, so I won't really get into why this kind of like everything works. The arguments are much the same, except you're working in a different basis, right? So if you're familiar with Lie algebra, all that's happening is we're working in a different basis. So all the results should carry over. Okay, so the interesting code that I really want to talk about before we end, I think I have about 10-15 minutes. So I should not take more than that. So let's talk about the short code. And let me already tell you that corrects a single arbitrary one qubit error, right? So you have, what you do is you have 0 being encoded into 9 qubits, right? There are 9 qubits here. There are three, these are 3 qubits, these are 3 qubits, these are 3 qubits. So what you have here is that k equals to 1 and n equals to 9, right? And this is kind of a weird structure, but if you look at the notebook, you will see how this structure is derived. I don't have time right now to go over it, but let's assume for a moment that this is a structure. You have a circuit that also creates this. That circuit is also that's one of the tasks in the notebook. You have to do it, but it's not difficult to create something like this. That 0 gets mapped onto these 9 qubits and 1 gets mapped onto these 9 qubits. The difference here is that, look, you have 0, 0, 0 plus 1, 1, 1, and you have 0, 0, 0 minus 1, 1, 1. And then these are just repeated, right? So you have this plus, plus, and then minus, minus over here. And obviously your arbitrary state, I mean, we can state just for clarity that if you, this is what Alice wants to send, right? It gets transformed into alpha 0 double bar plus beta 1 double bar. The reason I'm using double bars is also explained in the notebooks. But it's again, it just means the encoded state, right? So this is my psi double bar, right? This is the code word that Alice sends to the channel. Now, why does this work? Okay, is the big question. So yeah, so there's a question, there's implied tensor product in the thing. Yes, obviously. So there are tensor products here, 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 and here. We don't write it because it gets confusing. So let me just copy these guys again. Actually, let me copy half these guys. Okay, so error, let's do some error analysis. Okay, so let's imagine X errors. What we're going to do is we're going to like apply different errors to these two states, right? Remember that the first guy is the encoding of the 0 state, and the second guy is the encoding of the 1 state. And if we show that these are correctable, then superpositions will also be correctable because of the linearity of quantum mechanics. So we'll just look at the correction of the basis states. So what I'm going to do is, instead of drawing any circuits, I'm just going to talk about at the high level what we want to do in terms of detecting where the error has occurred, right? Remember that if I can identify where, for example, an X error has occurred, if I have a process that tells me where the X error has occurred, then I can very easily correct it by applying an X gate on that qubit. Similarly, if I know where a Z error has occurred, then I can apply a Z gate on that qubit to fix it, and then I can decode back to whatever message Alice sent. So let's look at this scenario. So what is the outcome of for example, let's pick x4. Okay. So for example, my error that occurs, so is x4, x4. Now, what is the impact of x4? X4 means that, you know, I have 0, 1, this is 0th qubit, 1 qubit, first qubit, and this is the 4th qubit. So this guy and this guy will get switched. So this will become a 1. This will become a 0. This will become a 1, right? And this will become a 0. Yeah, so there are no questions. So let me, so suppose, look at this. So how can I look at expression like this and figure out where the errors occurred? What sort of high level process do I do? And you've already done this for the previous code. Like, I'm not asking for a new process. What is the kind of process that we do? If anybody has guesses on that? Well, I mean, we have to come up with a process which works generically for any possible error, right? Here, I'm just giving an example of x4 just to give you an idea that, hey, this is this is the kind how the state will change. But we need a process that works for, we don't know where the error is. So we have to input a process that tells us where the error is, right? So we have to do something on every kind of qubit. So you're thinking of CNOT gates, but think about it at a high level. What did we do before? So what we did in the classical repetition case, that we said that we are going to compare the value of bits, right? The first and the second and the second and the third. And that tells us where the error is. In the quantum error correcting example, we did the same thing. We said that we will compare the value of the bits. We will look at this syndrome measurement circuit was comparing the value of the first and the second and third qubits. And that is what gave us the answer, right? So forgetting about the gates, just think about the high level process. That's exactly what we're going to do again. That we are going to compare, to detect X errors, we are going to compare the value of adjacent qubits, okay, in each of these blocks. So what we will do is, we will compare the value of the first 2 qubits. So this block of 3 qubits, right? I'm going to say, hey, is the value of the first 2 qubits the same? And you can see that in this example of x4 error, 0 is equal to 0, 1 is equal to 1, 0 is equal to 0, 1 equals to 1, right? So the first 2 qubits are the same. Then I'll ask the question, is the second and the third qubit the same? Again, you can see that in this block of 4, in all the terms, the second and the third qubit are the same. So in all of those cases, my syndrome will still be 0, because nothing is like, I'm getting same value. But then when I come over here in this second block and I'll ask myself, is the 4th qubit equal to the 5th qubit? I'll discover a problem. I'll discover that they're different, right? In all 4 of these terms, the 4th qubit is different from the 5th qubit. Then I ask myself the question, is the 5th qubit different from the 6th qubit? So I'll compare these two guys and these two guys, these two guys, these two guys, right? The second and third qubits in this block. And I'll discover they're all the same, right? 0 is equal to 0, 1 is equal to 1. So from that, I will immediately infer, hey, it must be the fifth qubit which is different. That's where the error must have occurred, because the value has changed. Okay. Yeah, so it's basically 3 copies of the previous circuit that we have. So we'll repeat that process in the third block as well. We'll compare the 6th and 7th and 7th and 8th qubits, and we'll see that that they're the same. So that allows us to uniquely identify where the error has occurred. Yeah, so we will, David, as Ron says, we will just we'll apply the quantum repetition code for bit flips circuit to 3 times, one to the first 3 guys, then to the next 3 guys, then to the next 3 guys. And that will tell us where the error has occurred. Now, these are X errors, right? I hope everybody agrees that this is, this kind of works. What about Z errors? This is oh, what did I do? Oh, I didn't. My mouse is there, and I just noticed it's here. When I copied this, I didn't even notice while I was talking about it that my mouse is staring everyone in the face. I'm sure everybody was annoyed about it. I'm just going to copy this again. I'm not going to replace the old ones, but this ones are clean. Okay. Sorry about that. I hope that when I was talking about it, these were not too much in the way. Yeah. So now error, for example, let's do the same thing. Let's apply Z4, Z4. What is the impact of Z4? Not a global phase. It's actually a local phase. Notice that Z4 will attack, Z4 will attack this qubit right here, right? The first qubit over here. And it will also attack this guy, it will attack this guy, it will attack this guy. When it attacks 0, nothing happens. But when it attacks this 1, this plus sign will become a minus sign. And similarly, when it attacks this one, this will become a plus sign. So that's the kind of thing that happens, that this disappears and I get a minus sign and I get a plus sign over here. Yeah, that attack signs. So now what is the high level process that we can do? Again, knowing that we are, like, if you can generalize from the previous case, what should we do to figure out where the error? Remember that, maybe it's worth noting that imagine this was Z5. Z5 actually attacks, the middle qubit over here. And that will also flip these signs. The impact of Z4 and Z5 are actually the same. In both cases, the middle qubits are the ones that are, these signs are getting flipped. It's the same sign that is flipped. Same for Z6, the last qubits over here. Again, these ones will flip, and you will get a minus here and a plus here. So, right, so Z4, Z5, Z6 are all doing the same thing. Similarly, Z0, Z1, Z2, Oh, Z1, maybe I should have. Yeah, so I mean, I'm using one indexing, I guess. The 1, 2, the first three Z on the first three qubits will also just flip this sign, and the Z on the last three qubits will also flip this sign. Okay, any of those. You're thinking about the circuit. Tell me the high level thing. What at high level, what are we comparing? What could we compare? What is the difference between this state and this state? It's this flips, right? So what sort of comparison do we do? Sure, I mean, it will be a control Z side of, we'll use control Z gates. But what we will basically do is we will compare the signs over here, the phases here. It's actually possible to ask ourselves a question in a quantum circuit that, hey, what is the phase of this and what is the phase? Are they different or are they the same? Are the phase of the first block and the phase of the second block, are they the same or different? This is a question you can ask in terms of quantum circuits. It's once you kind of work your way through for the repetition code for phase flips, you will see how that works. We didn't have time to go over it, but I mean, it's in the notebook. And you'll see that you can construct that circuit and you can ask yourself, what is the phase over here? What is the phase over here? Are they same or different? And in this scenario, they'll be different, right? And then you can ask yourself the question, or state the question, is the phase in the second block different from the phase in the third block? And again, the answer will be it's different, which will tell you that the phase in the middle is different. Okay, the middle block is where some sort of Z error occurred. Okay, I hope that makes sense. Yay or nay? Does that make sense? Can I get some sort of response in Discord just to know that I've not lost people? Yeah. Okay, great. So then if you understand it, what is the correction? What is my correction? Suppose I've discovered that it's the second phase which is incorrect. How do I correct it? Okay, so the correction is just Z4 or Z5 or Z6. It actually doesn't matter. Notice that if I apply Z4 again, right, I've discovered that the phase in the middle guy is different from the phase in the other two guys. So this is the one that needs to be corrected. So I can apply either three of these gates. One of them is sufficient. Even if I apply Z5, the error was Z4, but if I apply Z5, still this phase will be flipped and I'll get back the correct state. I can also apply Z6 and that will also correct the state. Actually, shortcode is quite interesting in this scenario. That, I mean, the error that occurs, the correction does not have to be equal to that. I can do whatever, like in the phase error case, at least I can just do whatever. Yeah, so let's now very quickly look at the last case, Y errors. So again, we said that y errors is just equal to zx, right? So the impact of, for example, y0 is equal to, right? You can see that y is just saying that, well, there's an overall iota sign that will just remain, and I'm just applying to the first guy, which tells me that both this phase will be flipped because of z, and these guys will be flipped, right? The first qubit will be flipped. Okay, so my Bob's process is first detect and correct X errors, then detect and Z errors. Notice what happens. There's a minus sign here, a plus sign here, there's an overall iota sign. That's a global phase, so we can kind of ignore it. So when Bob first detects and corrects X errors, right? So this phase in the middle, which is a problem, is not a problem at all for the X correction process, right? In the X correction process, we're only comparing the values of the qubits themselves. We're not looking at the phase at all. So it doesn't matter whether there was a phase flip here or not. Bob will notice that the first 0th qubit is different from the first qubit. So he will correct, and he will set this back to 000 minus 111 and 000 plus 111, right? The phase error will remain, but he can correct the X errors without any problem. And then once he has corrected the X errors, then he looks at the Z errors, and then he says, hey, what is the phase of the different blocks? And then he will be able to correct the Z errors. So Y errors will also be correctable in this way. Oh, I really love Pablo. Yes, Y is a bit flip and a sign attack. Yes. So okay, so I will leave you guys with one final kind of thing, that you'll notice something more strange about it, that Shor code. Shor code is named after Peter Shor, who's a very famous. Well, I guess everybody knows about the Shor algorithm for factorization. So it's the same Shor. He also invented this code, so that's why it's called Shor's code. Can correct some, but not all 2-qubit errors. Okay. So what I mean is that you can actually there are 2-qubit errors that are correctable. Okay. So can somebody give me an example of a 2-qubit error that will actually be corrected in the process that we have just given, where you first do X error correction or bit flip error correction by looking at each of these blocks and comparing the values, and then looking at phase errors. And when I say a 2-qubit error, so I mean that 2 qubits have independently have had an error. So maybe the first qubit and the 7th qubit have an error or something like that, and the first or the second qubit has an error. And you have to tell me what the errors should be. Is it an X error on the first qubit and a Z error in the second qubit, something like that. So sure. So David, you have an answer, but is it a X and a Z or what? Sure. So that is an example, qubit 1 X and qubit 4 Z, right? And also, so example is X0. Sorry, let's use 1 indexing. So even though in the notebooks I use 0 indexing, but I have kind of committed to this. So if my error is this, my error is X1 Z4, that means that this, and Z4 will flip this sign and flip this sign. So you can see that when I go through my X or Bob goes through the X correction process, he will just compare the values of the qubits here, and he will realize, and he will correct this, right? This is completely separate from this. And then he will compare the values of the phases in the second part, and then he will realize that this phase is off, so then he will correct it. So this is an example of a 2-qubit error that can be corrected, right? So can be corrected. Okay, but now I want you to just tell me an example of something that cannot be corrected, 2-qubit error. Yeah, so Adonso has a great answer. X1, X2, right? X1, X2 will, what it will do is it will do the same kind of mess up that happened in the repetition code for bit flips, that it will flip 2 qubits in one block, and then we will make a incorrect estimation. We'll do our error correction process for X, and we will incorrectly assume that it is the third qubit over here that is the wrong one, and we'll apply X3 as our error correction instead of X1, X2. So that's one example. And any other example? What is the Z analog of this? So can I do a 2-qubit Z errors, Z on both 2 qubits, which will, but which two? Which two will result in a incorrect correction? No, 4 and 5 Z will not work, because 4 and 5 actually, 4 and 5 is beautiful. I want you to realize that if 4 and 5 have an error, okay, so if 4 and 5 both, if I put a Z5 over here, then I'll actually get 2 flips inside here, and actually I'll get no error. This will go back from, this will remain a plus, and this will become a minus. So actually, this is another feature of shortcode, that there are actually errors which actually don't affect the state at all, besides the identity. The identity doesn't affect the state, but Z4, Z5 also doesn't affect your code word at all. It's actually equivalent to identity on your code word. So I mean, you see why this is beautiful. So Adonso has the correct answer again, that if I apply Z1, Z4, for example, right, then that means that the same idea, that I will flip the signs in the first block and the second block, right? All of these signs will be flipped. And that means that I will again incorrectly estimate, because these will both be minus and this will be plus. So I'll say, oh, the first two guys are the same, but the second and third guy are different. So it must be that it's the third flip that was wrong, and I should maybe apply Z9 or 8 or 7 to correct the phase flip in the last guy. And then I'll get minus, 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 and plus, plus, plus as my corrected or incorrectly corrected code word. So these are examples. You can think of other examples as well. You can also think of 3-qubit errors that are actually correctable by shortcode. So it's a very interesting code, like, and when you play with it, you will you really enjoy it. So at this point, I should stop. I think I've gone quite a bit over time. I should not really be doing lectures this long. So let me just review, and in the meantime, you can ask questions of what we have done. So the things we have done is that we learned that in the classical repetition code, what we do is we do this comparison of bits allows us to construct a parity check matrix. Using this idea of this comparison, we constructed a quantum error correcting code in which we just repeated a value of a qubit 3 times. Well, not the value of the qubit. We just converted something like alpha 0 plus beta 1 to alpha 0 0 plus beta 1 1. There's a pseudo repetition here that we did, and then we applied the same idea of comparison of qubits to figure out where the error was. And then we did the same thing for phase flips, where we said that instead we'll move to the plus minus spaces and we'll do the same thing. And because of by virtue of plus minus spaces, the way that Z acts on it, it's the same as how X acts on the 0 1 basis. So it will actually correct things here perfectly. And then we looked at the shortcode, which actually is able to correct any single arbitrary 1-qubit error. It can also correct some 2-qubit errors and 3-qubit errors as well, actually some higher ones as well. But it cannot correct all 2-qubit errors, which is why that we say that it is guaranteed to only correct 1-qubit errors. So yes, so Mohammad Raza, there are other examples as well, and you should just, I mean, an interesting exercise, I think, the exercise in symmetry and combinatorics is to just think of all the possibilities, like characterize all the cases which are correctable and which are not correctable. Okay, so I should stop now. What is the maximum of n-qubit errors short can qubit? You mean, so it is only guaranteed to correct all 1-qubit errors. If you're asking what is the example of the largest number of qubits which can experience error that Shor can also correct, I don't remember off the top of my head. You can compute it yourself. And perhaps post it in the QEC channel once you figure it out. Yeah. Okay, thank you to you as well. I will stop sharing.
Wonderful. Thanks a lot, Abdullah. Great session as always. And I guess the participants are still busy on the Discord channel having a great discussion. They might also have some follow-up doubts. So again, I would just request them to continue their discussion. And once this live lecture is over, continue your discussion in the QAC channel as well. And Abdullah is also on Discord, so he can answer your doubts over there as well.
Absolutely. Thank you so much.